Okay, so we need to have a look at particle theory. So a quick recap of particle theory from Key Stage 3. So we've got a solid, liquid and a gas. The particles in a solid are all bonded together, so they can't move as individual particles, so they just vibrate in a fixed place. They vibrate because they've got energy. In a liquid, what we have is some bonds. We've got fewer bonds. They're not all bonded together, so the little clusters or clumps of particles can tumble about over each other because they're not all bonded together. So we call this jostling, so they will jostle. When we're talking about particles, we're just talking about things like atoms, ions and molecules, so we're just using a general generic term for particles. But if we're talking about atoms or ions and molecules in more detail later, it's just the same thing. So particles in a gas, what's happened here, we've got 3 rows of 3 for the solid, 3 rows of 3 for the liquid, but the gas particles, I've shown them, they bust out the box, they've exploded and they can go anywhere they want. Why? Because the particles are not bonded to any other particles, so these can move freely. Again, one of the things that they want you to think about is this concept from Key Stage 3, again, that we've got change of state from a solid, a liquid to a gas. So the best example you can use is water. So we know about ice water, and then liquid water and steam. So how do you get from one to the other? Well, you heat ice cubes up and they will melt and turn into liquid water. So heat up, melt. Heat the water up to the appropriate point, so in this case for water it would be 100 degrees C. You would get to the boiling point. If you cool it down from a gas to a liquid, that's called condensing, and then cooling down further from the liquid to a solid is called freezing. Again, just think about what the particles are doing. So in the solid particles, they're all bonded together, vibrating, and the liquid particles are all sort of moving about, tumbling over each other because they're not all bonded together. And then the gas particles can move freely. We've got, flying about everywhere. Okay, so one of the other things that they want you to think about is how we get those changes of state, how it's represented on a graph. So if we've got, let's take water again. So if we've got a temperature on the y-axis of 0 degrees, we know that that's the melting point, it's also the freezing point, depending on which way you're going. So if we're going from right to left on this graph, on the x-axis, we're heating up. So if we were going from right to left and we're heating up, it would melt. If we're going the other way, if we're cooling it down, it would freeze at 0 degrees. If we increase the temperature of the liquid that we form when we melt it to 100 degrees, then we start to boil. So we've got the idea that below 0 degrees, it's a solid. So and if we're below 0 degrees, for water, we would have a solid. Between 0 and 100, so between these two temperatures, we've got a liquid. But if we go over its boiling point, which is 100 degrees, we will have a gas. One final thing to note, and they do ask you about this, it's this sort of plateau where the graph doesn't actually increase, even though we're cooling down or heating up, where there's no temperature change. That is when bonds are broken or bonds are made. So that's actually when the change of state occurs, at this point. So if we were to think about, okay, when does it actually start melting? It's going to be at this point when it starts melting. And when does it finish melting? When it's turned completely into a liquid, here. Okay, the same for boiling. When does it actually start boiling? Here. And when does it finish boiling and turn completely into a gas? It's here. So there's no change in temperature. It's just that it will sort of plateau or flatline. And what's happening there is bonds are broken or bonds are being made. And now we move on to separation techniques or separating mixtures. As soon as you hear the word mixtures, you can think about separating them. Mixtures are made of particles that are not chemically bonded together, so we can separate them using physical methods. So the four main that you think about, the four main separation techniques: filtration, distillation, recrystallization and chromatography. And it's fairly straightforward, it's fairly self-explanatory, so we'll do each one in turn. So here we've got filtration, and you use filtration to separate an insoluble solid from a liquid. So this could be as simple as sand away from water. So sand would be the insoluble solid and the liquid would be water. So if we've got a mixture of sand and water, initially the particles look like this. They do want you to think about the particles in that mixture. So we've got different coloured particles to indicate we've got a mixture. The liquid particles are not all bonded together, but we've got sort of rogue sand particles within that. When we pass it through the filtration, we use this filtration apparatus. We have a flask, a filter funnel and filter paper. The filter paper will trap the solid particles but allow the liquid particles to flow through. The solid particles that we trap are called the residue, and the liquid particles that drip through are called it's called the filtrate. So that's how we separate them. So when we think about it, what would we have? We would have all particles in the solid would be the same, and all particles in the liquid would be the same because we've separated them out, and that's key. So they would want you to sort of be thinking about things in terms of the whole idea is separating the mixture that we have here on the left, and we've separated them out into only the sand particles and only the liquid particles. With distillation, distillation is another separation technique, and we're going to separate a mixture of liquids with different boiling points. Distillation can be used for separating fluids, so gases you can distill air. It's how we get sort of individual gases like oxygen and nitrogen and whatnot. But the one that we're more familiar with is the distillation of liquids. So it could be the distillation of ink and water, or whatever. But again, it's just thinking about this idea of a mixture. So in the box here we've got a mixture of blue and orange liquids. Okay, it exploits the fact that they will have different boiling points. So what we need to do is heat, and when we heat the mixture, one of them with the lowest boiling point will evaporate. So in this case we've got the orange particles are gaseous orange particles, whatever that is. The green particles, now we've managed to separate them, but what we need to do is try and collect the orange particles. The orange particles are gaseous because we've heated them up. We turn them from a liquid to a gas. So what do we need to do now? We pass them through the condenser. The condenser will cool the gas and condense it, turn it back into a liquid. The key thing to remember with the condenser is that the water goes in at the bottom and the water comes out at the top. So it goes in cool and comes out a little bit warmer. And what the condenser does is turn it back into a liquid, and we collect the liquid. So you can see here we've separated the original mixture of green and orange particles, and we've left the green particles that had a higher boiling point, and we've collected the orange particles that had the lower boiling point. Recrystallization is even easier because we're going to separate a soluble solid from a liquid. So in here, the one that they really ask you to think about is copper sulfate. So recrystallizing copper sulfate. So in the evaporating dish at the moment, we've got a mixture of copper sulfate particles, which are blue, and then the water particles, which I've coloured in white. So all we need to do there is either apply some heat or just let it evaporate naturally. So when it evaporates, the water with the lower boiling point just escapes, forms a gas, and then what we're left with at the bottom, if you can see it, are solid crystals of copper sulfate. And that's how we separate them. And in this case, it's very similar to distillation, but we're not making an attempt to reclaim the evaporated gas. We're not bothered. We just let the water escape. Final one we're looking at is chromatography. So the key thing here, chromatography is all about colours. It's based on the Greek word for colour. There are more difficult or more interesting or more technical types of chromatography, but we deal with the basic one, which is basically splitting up colours. So we're separating a mixture into its different components. So first we draw a pencil line because ink would smudge. Then we put the dots of our ink samples on. Now ink is a mixture of different dyes. So once we've got that ready, we will drop that into some water, and then the water sort of creeps up by capillary attraction, or however you want to think of it. As soon as it's got to the top, what we need to do is take it out of the water and then draw a second pencil line, and that's the solvent front. So really what they might ask you to do is how many different sort of dyes were in the original inks. So here we've got an ink that is separated into 1, 2, 3 dyes, this separated into 1, 2, and this separated into 1, 2 as well. So this has got the most components, or it's got 3 as opposed to 2 and 2. The other thing they might ask you to do is identify, well, are there any common dyes within those inks? And we can see here that the 2 red samples, because they've got to the same point, they're going to be the same dyes. One final thing they might ask you to do is calculate the RF value. The RF value is just an idea of how far the ink splodge or the spot has gone compared to the solvent. So you measure out the solvent front, in this case it's 8 centimeters, and then you measure out from the pencil line to the middle of the spot. So pencil line to pencil line for the solvent front, pencil line to the middle of the spot that you're interested in this case 3, and then you just do a quick calculation. So the RF value is actually this blue spot has made it up 3 centimeters out of the total 8 that the solvent went. So it's 3 divided by 8, which gives us an RF value of 0.375. I think the notes here, the notes should be fairly straightforward. What we need to be thinking about is link the particle theory sort of diagrams, and you can draw them out at any point. Link the particle theory diagrams for the solid, liquid and gas to actually separation techniques. Okay, there's an A in separate. Okay, so separate. So separation techniques, link it. Always refer back. If they're talking about, if they ask you in terms of particles, you need to talk about, again, solid, liquids and gas, and the particles there, and the diagrams and everything like that. Okay, good luck.